So, welcome everybody. I'm going to speak for the next hour about the use of multiple antennas within 5G systems, focusing upon the use of beamforming and massive MIMO. It can be a bit of a difficult subject. It is difficult to get descriptions which are, on the one hand, not completely inane, and on the other hand, not deeply mathematical. I will try my best to strike a balance, but nonetheless without including very much maths. I will begin by introducing the use of multiple antennas within 5G, speaking about what they're used for and introducing the main techniques. I will then speak about beamforming, which is used to improve the coverage of the system, typically at high radio frequencies. Building upon that, I will speak about the use of multiple input, multiple output MIMO antennas, which are to improve the capacity of the system, typically at low radio frequencies. And I will close with some thoughts on deployment issues and performance issues within 5G. So let's begin with looking at the fundamental techniques that we're going to be using. I think a good introductory slide is one speaking about the usage of radio spectrum within a 5G system. Just pulling up my annotation toolbar here so that I can show you what's going on. We have got here frequency running from left to right. 5G is intended to operate in two separate frequency bands, number 1 and number 2. Frequency range number 1 overlaps with the frequencies previously used by LTE systems, typically 1 up to 4 gigahertz or thereabouts. Frequency range 2 is at frequencies of tens of gigahertz, often known as millimeter waves because of their radio frequency. Frequency range 1 has traditionally been, and still is, the most popular. It gives really good coverage in that the radio signals can be successfully received from a long way away. And yet the capacity of the system is not so great. The capacity of a radio system depends upon the amount of radio spectrum, the amount of bandwidth which it occupies. Down at these low radio frequencies, the amount of radio spectrum available is not so great, so the system capacity is not so great. Up at the very high frequencies, the opposite problem arises. There's loads of radio spectrum available, loads of bandwidth, so the capacity of the system is potentially nice and high. However, it is difficult to receive the radio signals if you're far away from the receiver. The reasons being somewhat subtle and technical and outside of this presentation, but nonetheless the problem of coverage exists. So we have two distinct scenarios. At low radio frequencies, the coverage is good. At high radio frequencies, the capacity is good. And two distinct problems. At low radio frequencies, the capacity of the system can be limiting. At high radio frequencies, the coverage of the system can be limiting. Well, the great thing about multiple antennas is that they can help with both of these problems. They can improve the coverage at high radio frequencies, and separately, they can improve the capacity at low radio frequencies. Let's introduce how. Perhaps I'll begin, I should begin by showing you the architectures, shouldn't I? I'm looking here, well, at both the uplink and the downlink, but let's describe it by reference to the downlink. Here we have a 5G base station and next generation node B. The base station is equipped with multiple antennas acting as transmitters within the downlink and receivers within the uplink. The first technique that we will use is beamforming. The action of beamforming is to get the antennas to work cooperatively together so as to focus the intensity of the radio beam towards the desired target upon the downlink, and to focus the reception beam towards the desired transmitter upon the uplink. And by focusing the signal energy in this way, it will improve the coverage of the system and thereby will deal with the problems encountered at high radio frequencies. MIMO, multiple input, multiple output antennas, is a slightly different technique. Here, we will set up multiple streams of information called layers, which can be sent in the downlink on the same radio frequency and at the same time, thereby improving the capacity of the system. We have a collection of variants, notably single user MIMO, multiple layers sent to a single user, multiple user MIMO, multiple layers sent to different users, but they all act to improve system capacity. And this once again can work in the uplink as well as the downlink, and this will improve the capacity of the system primarily at low radio frequencies. The techniques used for MIMO build upon the techniques used for beamforming, so I'm going to talk about beamforming first and MIMO second. So we'll move to beamforming. In this slide, I'm going to talk you through the principles of what's going on. My descriptions will nearly all relate to the downlink, but please keep in the back of your minds that all of these techniques will work just as well upon the uplink. Here we have a base station, a next generation node B, equipped with a large number of antennas. Typically, we imagine the antennas being half a wavelength apart. So say at a frequency of 3 gigahertz, fairly typical, then that's about 50 millimeters apart, that kind of thing. We are going to try to communicate towards mobile number 1, shown here with the text in blue. Hidden assumption: mobile number 1 is assumed to be a long way from the base station, such that these little radio waves here are heading towards mobile number 1 and they're coming out parallel with each other. Mobile number 1 very distant. So we have got there a base station with multiple antennas, and we're trying to transmit towards mobile number 1. It will be rather good, I'm sure you'll agree, if the little radio waves originating from each of these antennas reach mobile number 1 in phase with each other, as shown, so that the peaks all coincide with each other and the troughs all coincide with each other, because then the radio waves will all reinforce and mobile number 1 will get a nice, strong received signal. Nonetheless, the path lengths to mobile number 1 are different. From the antenna at the top, the signal has further to travel than it does from the antenna at the bottom. We can compensate for that by introducing phase shifts into the transmitted signals. The phase shifts introduced here and becoming apparent here, so that we apply the exact phase shifts which are needed to make the peaks and the troughs of these radio waves coincide. With the antennas assumed to be equally spaced, as is nearly always the case, actually there's just a single parameter to apply, which is the phase difference from one antenna to the next, denoted by the Greek letter phi. Sorry to get Greek here, apologies, kind of standard notation. So you apply a little phase difference in the transmitted signal, which you add in successively from one antenna to the next, kind of like a phase ramp, and the radio waves come out in the way that you need. Now, viewed from mobile number one, that all works fine, but how about if we viewed the radio waves from a different direction? For example, mobile number two, also a long way from the base station. Viewed from this mobile, the radio waves are going to cancel out. The geometry is somewhat different. And indeed, viewed from this precise direction, the radio wave at the top will cancel out completely with the next but one wave down. And this radio wave will cancel out with this one. All the radio waves will mutually cancel out, and mobile number two will receive nothing at all. At intermediate directions, there might be partial reinforcement and partial cancellation. So what's the effect of all this? The effect is that we have created an artificial electronically synthesized antenna beam with a main beam pointing towards mobile number one, a null here pointing towards mobile number two, and other nulls and side lobes in between. For those who are happy with the maths, that's the width of the main radio beam, and this is the desired phase shift depending upon where you want, when the mobile number one is. The effect of all this is to focus our transmitted signal energy towards mobile number one. Instead of the energy splaying out equally in all directions, it is now focused towards mobile number one, which therefore gets a really strong signal. Mobile number one can now receive the signal from really far away, and we have solved the coverage problems which arise at high radio frequencies, focusing the beam towards mobile number one. And it works just as well on the uplink because we can focus the reception beam towards mobile number one and pick up a strong signal from it. So that's the basic principles. The next question arises then of how do we steer the beam? After all, if mobile number one moves around, then we will want to apply a different phase shift, phi, between the antennas, so as to direct the main beam towards mobile number one. Now, you could do it by calculating the exact analog phase shift, phi, that would be required, and steering the beam accordingly. But that would require a revolting analog control loop, which is something we really want to avoid. There are a few ways of getting round that problem. Three main techniques, as denoted here. The first and simplest technique I'll look at is analog beam selection, which tends to be good at high radio frequencies. The second technique is what we call digital pre-coding, which tends to be good at low radio frequencies. And the third technique is an intermediate case, a mix of analog and digital known as hybrid beamforming, which, perhaps no surprise, can be good at intermediate frequencies. So let's have a look then at analog beam selection. Key features of this technique. It's simple, a little bit inflexible, however. The power consumption is nice and low, which is good. And it's used at high radio frequencies, typically, for example, millimeter waves. As in the previous slide, we will equip the base station with multiple antennas, with the signals to each antenna adjusted by means of analog phase shifts. I have then explicitly shown a single digital to analog converter at this point here. However, we won't allow the beam direction to vary continuously. Instead, we will set up a discrete set of beams, 1, 2, 3, 4, 5, as shown here, with those beams created using a discrete set of analog phase shifts. We will not allow the phase shift to vary continuously. It's going to change in jumps, with each jump corresponding to a switch to a different beam. We will typically set up these beams so that the main lobe of one beam coincides with the nulls of the beams next door. Here, for example, the main lobe of beam number 6, highlighted, coincides with nulls of beam number 5 and of beam number 7. And by doing that, we can get pretty good coverage everywhere. One feature, the base station can only transmit in one beam at a time. There's not enough digital capability to do multiple beams, so we're going to switch from one beam to the next by means of time division multiplexing. Transmit for a bit in beam number 1, and then beam number 2, and so on and so forth. Just going to briefly checking on what's appearing in the chat window there. Each beam is going to be labeled with its identity. Within each beam, there's going to be a little signal getting transmitted. I'm beam number 1, I'm beam number 2, I'm beam number 3, and so forth. And within different places within the 5G system, those identities have different names. So, to transmit to this mobile here, the base station does so within beam number 6. That's fine. The mobile, meanwhile, will measure the identity of the best beam which it is receiving. And if mobile moves around, then it might need to send some feedback to the base station to say, hi base station, I'm not in beam number 6 anymore, I'm in beam number 5. Could you please transmit to me using beam number 5? That feedback happens to be called the CSI, the Channel State Information Reference Signal Resource Indicator. This then is a nice simple technique. One parameter, the phase shift, or the beam identity, one parameter fed back from the mobile, which is the best beam. Nice and simple. A little bit inflexible, as we'll see. One big advantage, however, is that the power consumption is reasonably low. It turns out that D to A and A to D converters can have a rather high power consumption, and that is a particular problem at high data rates where the digitization rate is rather high, and that tends to happen at high radio frequencies. So we can say power consumption is a particular problem at high radio frequencies because of the data rates and the D2A converters which are involved. This technique is simple and limits the power consumption and is good at high radio frequencies, for example, at millimeter waves. Let's be a bit more clever. Digital beamforming. We're going to take the block diagram from the previous slide, and instead of applying a single D2A converter here, we're going to apply one D2A converter in each individual transmit antenna. We can then manipulate the signals in each antenna digitally using these weights here. They're called pre-coding weights. And now it's not a single parameter total. It is actually two parameters for each individual antenna, because at each individual antenna, we can adjust the phase of the signal and the amplitude of the signal that's going through it. And that gives us much, much more control over the beam. It allows us to steer the main beam and the nulls and the side lobes in more or less whichever direction we please. Here's an example. We could steer this main beam directly towards a target mobile, while also steering a null towards a victim mobile, maybe in another cell, which might be vulnerable to interference. So this is now an awful lot more powerful. The feedback is a lot more complicated. The mobile sends some feedback to the base station called the PMI, which essentially tells the base station about the best set of antenna weights to use so as to steer the main beam towards it. PMI happens to stand for pre-coding matrix indicator. You end up with some matrix multiplication going on here, which the mathematicians amongst you will enjoy, and for the non-mathematicians amongst you, I will try to avoid as best I can. Digital beamforming, then. It's more complicated. Particularly, this feedback is complicated. It is, however, more powerful, more capable. The power consumption of this can be a lot greater. We have one digital to analog converter for each individual antenna. And if this were used at very high radio frequencies, then the power consumption would be excessive. So we would tend to use this as is, usually just at the lowest radio frequencies, for example, within a 700 megahertz band. Perhaps no surprise that there is an intermediate technique which can sometimes get the best of both worlds. It's called hybrid beamforming, and it uses a mix of analog and digital techniques. There's various ways to do it, but a common scenario is shown in the diagram on the left. Here we're setting up a base station with a number of different antenna panels. So each of these pale blue blobs is a panel. To each panel, we have a stream of stuff which has been digitally pre-coded. There is one D2A converter per panel. And then within each panel, we will apply analog phase shifts for the signals transmitted within each panel using the techniques from the previous slide. Perhaps no surprise then that this technique gives us something which is intermediate in terms of complexity and performance and power consumption. Briefly, the narrowly spaced antennas within a panel give us wide, large-scale beams, denoted here, through which the base station will need to switch from one to another by means of analog beam sweeping. The widely spaced panels give us narrow, digitally controlled beams within each of the wider beams, and we can use those narrow, digitally controlled beams for the cleverer techniques that we denoted within the previous slide. So together, this gives us some of the flexibility from the pure digital solution, although not all of it. The intermediate complexity and intermediate power consumption make this suitable for intermediate frequencies, for example, the 3500 megahertz band. I have been describing all of this with relation to the base station, but actually we can do beamforming at the mobile as well. There's a few differences. Perhaps one important difference is that mobiles can change their orientation, and that can make things a little bit more complicated. Furthermore, mobiles want to be nice, cheap devices to be built nice and cheaply, so we want to keep the techniques used relatively simple without too much sophistication. This is the typical scenario. We would set up separate antenna panels upon the mobile and have the mobile switching from one panel to another as its orientation changes. That is essentially an analog technique. And then within each panel, we might have multiple antennas which could be controlled digitally to create a steerable beam. That would be quite a sophisticated mobile. A mobile could, at a simpler level, use analog-only techniques throughout. This does, however, make the process of analog beam selection somewhat more complicated, because the base station and the mobile have to together hit upon the best pair of beams to use. The base station has to sweep through its analog controlled beams, and the mobile has to swap between its analog controlled beams until they hit upon the best combination. Needless to say, the control algorithms that are assumed within the specifications for 5G get a wee bit complicated, but this at least is the principle of the whole thing. So that, I think, is beamforming covered. And the whole point of beamforming then is that we can use multiple antennas to focus a beam towards a desired receiver, improve the received signal power, and thereby improve the coverage of the system. So let's now move on to MIMO, the use of multiple input, multiple output antennas. To do that, we're going to build upon the techniques of digital beamforming from the previous couple of slides ago, but we're going to use that not to improve coverage, but to improve the capacity of the system. I'm going to illustrate it using this slide here, downlink multiple user MIMO. For those who are a bit familiar with MIMO, you may know that this was a later technique to be introduced. It came in later than single user MIMO. Nonetheless, I'm doing it first because it fits more clearly with the beamforming matters that we have covered to date. I'm looking at the downlink, and let us focus first of all upon the blue lines, which are pointing towards mobile number 1 at the bottom right. Looking at the blue lines alone, this is simply digital beamforming. We've got a base station with 4 antennas, each with a D2A converter. We have applied pre-coding weights to the antennas to adjust each of the amplitudes and phases individually. And by doing that, we have got 4 blue rays traveling towards mobile number 1, which will arrive in phase with each other, thereby creating a main beam which points towards mobile number 1. At the same time, using our digital beamforming techniques, we are going to arrange for a null of the blue beam to be directed towards mobile number 2 at the top right, so that mobile number 2 picks up no interference at all. Also, in parallel, using the red lines, we're going to do exactly the same thing in respect of mobile number 2. So we're going to set up a digital beamforming system, which directs a main beam towards mobile number 2 and a null towards mobile number 1 by using the red pre-coding weights. And by doing that, we can send some information to mobile number 1 on the blue lines, and we can send information towards mobile number 2 on the red lines. And now, the cunning thing that we're going to do is we're going to send these 2 pieces of information on the same radio frequency and at the same time by the simple technique of adding together the 2 transmitted data streams at each antenna, as depicted by these addition symbols here. In doing that, the base station will send out both of these antenna beams on the same frequency and at the same time, and will transmit those pieces of information to mobile 1 and mobile 2 on the same frequency and at the same time. And it does work honest. Okay, the transmitted information includes information for mobile 1 and information for mobile 2. Nonetheless, as viewed from mobile number 1, all of the information directed to mobile 2 cancels itself out, and mobile 1 only sees the information intended for mobile 1. No interference. Likewise, at mobile 2, all the information directed towards mobile 1 cancels itself out, and mobile 2 only sees the information directed to mobile 2. And by doing that, we have successfully sent and received 2 pieces of information at the same time, and we have thereby doubled the capacity of the system. And that is the basics of multiple user MIMO. I've described this, by the way, by directing the null of this blue beam directly towards mobile number 2. That is By itself, that only accounts for interference. One probably wants to account for noise as well. And if you do account for noise, you probably end up doing things a little bit differently. And then you get into issues about the various types of precoder which you end up with. The situation described in the slide is a so-called zero forcing precoder, which points the nulls in the exact right place, and it's the easiest one to understand. And let me also just highlight, as with all of the other slides, but this is the only one I'm actually showing, this works just as well in the uplink as well as the downlink, in that the two mobiles will transmit on the same frequency and at the same time. The signals arrive at the base station and they can be processed by two parallel sets of so-called post-coding weights, so as to maximize the signal to noise and interference ratios which arrive from mobile number 1 and from mobile number 2. Let's just go back to this downlink slide for a moment. You might think, hey, fantastic, all our capacity problems solved. Well, it ain't quite as simple as that, I'm afraid. This works fine with 2 mobiles in the cell. But imagine what would happen if we had 10 mobiles within the cell. We would want to create a blue beam with a main lobe towards mobile 1 and nulls towards mobiles 2, 3, 4, 5, 6, 7, 8, 9, and 10. Meanwhile, we want to create a red beam with a main lobe towards mobile 2 and nulls towards mobiles 1, 3, 5, 6, 7, 8, 9, and 10, and 4 as well. And so on and so on. Although this works well for 2 mobiles, if you try doing it with 10 mobiles, it's all going to go horribly wrong, because you're never going to steer the nulls in the exact direction you want them. You're always going to get some interference leaking through. And if you have too many mobiles, then the interference levels are just going to make it completely unworkable. And indeed, this all works okay if the number of mobiles in the cell is small, like 2. But as the number of mobiles participating increases, it all breaks down. Fortunately, there is a workaround. The workaround is massive MIMO. Let me just put one important feature of massive MIMO at the top here. I'm not doing too many of these because it's an hour-long webinar, but let us actually write down the key feature at the top is that the number of base station antennas is much bigger than the number of participating mobiles, which is itself much bigger than 1. Previously then, we had just, I think, 4 base station antennas. Here, we're going to have lots of base station antennas. And just for the illustration, we have a base station with 16 antennas transmitting to 3 different devices, which hopefully satisfies this key defining feature at the top. It turns out that as you add more and more antennas to the base station, so the received signal power becomes better and better focused around the target mobile, and less energy is wasted elsewhere. The technique works best in a rich multipath environment, loads of reflections of loads of reflectors. And in that situation, the mobile is illuminated from all sides, and the received signal ends up as a sort of a patch, a small patch around the mobile, and most of the energy ends up focused within that small patch, and less energy is wasted elsewhere. It also works okay in line of sight environments, but lots of multipath is best. More antennas, better focused received signal, less energy wasted elsewhere. That then does two really good things for us. The first is that with the signal energy focused around the target mobile, then the received signal to noise ratio increases. That's good by itself. It can increase your data rates, but it also means that the transmit power of the base station can fall while keeping the SNR okay. And that in turn means that the electrical power consumption within the base station can fall. Now, the operators of radio access networks have been, over the years, getting more and more worried about the electrical power consumption of their systems and spending loads of money paying the electricity companies for the power. Massive MIMO is then a technique which, by focusing the signal energy at the target device, allows you to waste less energy elsewhere and wind down your transmit power and wind down your electrical power consumption while still getting satisfactory reception. And the second issue is that if you start adding other participating mobiles in a multiple user MIMO situation, those mobiles will get a higher received signal to interference ratio, because this yellow mobile here is picking up less interference spilled from the red mobile up at the top. So we can add mobiles in without worrying. Essentially, compared with the previous description of multiple user MIMO, the side lobes are now sufficiently low that we don't have to worry about them anymore, and we don't really need to steer the nulls anymore. We can just plonk the mobiles wherever we like. The side lobes are low, so the interference is low. And that then allows the base station to add more participating mobiles on the same radio frequency at the same time. And that improves the capacity of the system, which is what we wanted to do at low radio frequencies where the spectrum is limited. So massive MIMO is essentially an adjustment of multiple user MIMO in which the base station has a large number of antennas. It allows you to reduce the electrical power consumed by the base station, which is good, and it allows you to transmit to multiple mobiles on the same frequency at the same time, thereby improving the capacity of the system. I've been speaking about multiple user MIMO, but single user MIMO is still used as well. The traditional way of looking at single user MIMO, which was the typical viewpoint in 4G, was of, on the downlink, a base station transmitting two separate pieces of information from two antennas. The mobile has two antennas to receive two pieces of information. Nonetheless, the information arriving at each receive antenna is, as depicted here, a linear combination of the two transmitted pieces of information. Nonetheless, the mobile can make two separate measurements at its two antennas, and by doing so, it can recover the two quantities previously unknown to it, the two transmitted pieces of information, essentially by solving a pair of simultaneous equations. Two simultaneous equations, two unknown quantities, you can find out what they are. That is the traditional way of looking at single-user MIMO. Well, you may very reasonably wonder, how on earth does this relate to the multiple-user MIMO picture that we have been describing? Thinking back to multiple-user MIMO, one base station sending two layers to two separate mobiles on the downlink. In single-user MIMO, the two receive antennas are upon a single device, not two devices anymore, they are on one device. That leads to a number of differences. The first difference, the first distinction, is that the mobile has access to both pieces of incoming information from the two antennas, not just one. Second distinction, the base station can't steer nulls towards antennas anymore because the antennas are way too close together. So, base station can't steer the nulls anymore. Both antennas are going to pick up something about everything that's arriving. However, the mobile has access to both antennas, so the mobile is capable of disentangling everything. The diagram shows the viewpoint. Here, a base station is going to transmit two separate layers, in other words, two separate data streams on the same radio frequency and at the same time. We assume that we are operating in a multipath environment, and the bottom line is that each layer is going to get mapped to a separate ray path. I guess in this diagram, we should assume that there is no direct ray, so there is some sort of an obstruction saying nothing direct is going to get across. And we then have two separate ray paths available from these two different building reflections here. And we are going to map one layer to each ray path. The red layer is getting mapped to the red layer ray path, and the blue layer is getting mapped to the blue ray path. The transmitter includes a precoder. The action of the precoder is to map the red layer to the red ray path, essentially directing a red beam out in this direction and ensuring that there is a null of the red beam pointing down here. Maybe in red, I could attempt to draw that. Let's see if this works. We're going to direct a red beam with a main beam pointing up there and a null pointing down there. Similarly, the precoder will set up a blue beam with a main beam pointing towards this obstruction, this reflector, and a red beam pointing up here. So we now have a one-to-one mapping between layers and beams. In the mobile receiver, the postcoder will do essentially the same thing for reception. The postcoder will extract the information from this ray path, this beam in red, and plonk it onto the red layer. And it will extract the information from the blue ray path, the blue beam, and plonk it onto the blue layer. And by doing that, we will send and receive two pieces of information on the same frequency and at the same time, thereby doubling the transmitted and received data rate. Same end result, just a different way of looking at it. The maximum number of layers that we can send and receive is limited by the number of ray paths which are available. So the mobile has to send feedback called the rank indication back to the base station transmitter to say, hey, base station, at the moment I can handle two separate layers. But if, for example, this ray path got obstructed, then the mobile would get confused and we would say, rank indication, can you cut down to just one layer, please? I have depicted this, by the way, as one layer per ray path. If we have multiple polarizations, then we may be able to get two layers per ray path by using those two different polarizations. So the data rates can be twice as high as depicted. So that's single user MIMO still used within 5G. A brief word about some of the performance and deployment issues before we close. This is just an example from an evaluation of a Sprint network in the USA. I think it's actually in an LTE network, but the same situation applies in the case of 5G. The source for this is a white paper published by 5G Americas on advanced antenna systems for 5G. This is LTE cells with a 20 megahertz radio bandwidth. I should say that this is depicting a high signal case with mobiles nice and close to the base station so that we are extracting just as much capacity out of this system as we would hope to do. But this does at least give an idea of the amount of performance improvement that one can expect. Upon the left, we have a system with 8 transmit antennas, 8 receive antennas, and 2-layer single user MIMO, giving a capacity of 160 megabits per second per sector. That being really only achievable in that kind of bandwidth if your received signal is nice and high. By switching to 64 transmitters and 64 receivers, it allows us to bring things up to 8 MIMO layers and allows us to greatly increase the data rate within the cell. Now you may say, okay, well, this is just a high signal situation, but we can also do this kind of thing with weaker signals as well. This is another scenario reported in the same white paper. On the horizontal axis, we're looking at the, let's say, the network capacity, the amount of traffic per unit area delivered within the system. On the vertical axis, we're looking at the throughput achievable by a user at the edge of a cell if one is going to be fussy, we would say, okay, scatter users at random about the system and look at the 5th percentile, in other words, the percentage of throughput below which 5% of the users would lie. Essentially, the top right of this picture is a good place to be because your cell edge data rates are high and your system capacities are high as well. So you want to be up at the top right. And we have measured performance with 2 transmitters at both ends, 4 transmitters at both ends, and 32 transmitters. And this nicely illustrates the kinds of performance improvements which can result. So astonishingly, I've got to the end of this webinar at roughly the intended time, 11 o'clock. I hope that it has given you some helpful insight into the action of beamforming and massive MIMO within 5G.